So, a couple other things that I want to mention in terms of viscosity. There are temperature effects, and so temperature can affect the viscosity. And if you look in the back of the book, for instance, the viscosity of water is given at a range of temperatures. And viscosity decreases with increasing temperature in fluids, but in liquids, sorry, I said that a little fast. Viscosity decreases with increasing temperature in liquids, but viscosity increases with increasing temperature for gases. So you need to be careful when you're having to deal with temperature effects and viscosity to make sure that you deal with the way that liquids and gases are different. Another thing that I want to just mention quickly is that you that some liquids, for many liquids, the viscosity will behave in this way. We'll have this sort of temperature dependence. And this equation can be used to interpolate the viscosity at any temperature, or at least where this equation is valid. And so I'm not going to do this, but I just wanted to show you basically how you deal with this. So you can take the natural log of both sides of that equation. So if you have, if you have mu equals C E B to the T, you can take the natural log of both sides of this equation. And this is going to be the natural log of C once you that's a large C, capital C, once you do some arithmetic involving logarithms, you get this equation. And what you can do then is you can basically, if you know the viscosity at two temperatures, let's say we knew the viscosity of water was 1.00 times 10 to the minus 3 Newton seconds meters squared at 293 Kelvin. And if we knew, let's call that mu1 and mu2, and we knew that it was 6.53, these come from table A5, times 10 to the minus 4 Newton seconds meters squared at 313, then we could basically plug these values in for these two, and we could subtract them, which would eliminate C, and we could solve for B. And then we could do substitution, just like we would for a linear equation. We could then use our value for B that we find by eliminating log of C, and we could find C by substituting back in. So let me just show you what I mean by that. If I can just write this out quickly, that the log of mu1 must equal, if this is, it's going to equal log of C, which is a constant, remember, plus B over temperature 1. In this case, it would be 293. And then we also have log of mu2 would be log of C plus B over temperature 2. And if we subtracted these two equations from each other, it would eliminate these, and we would have log of mu1 minus log of mu2 equal to B over T1 minus B over T2, and we could use that to solve for B. And then what we would do is substitute back in to one of these equations up here. Substitute B back in, and then solve for C. So we have a way of getting these constants, and once we have both B and C, we can determine the viscosity at any temperature by this equation again, by knowing what temperature we want and then solving for the viscosity. Okay, so that's how we might deal with viscosity effects. Okay, so for gases, An estimate of the variation of gas viscosity with temperature can be given by Sutherland's equation. And Sutherland's equation here is given here as the ratio of mu over mu naught, and then this temperature dependence here plus S. And so what do these things all mean? Mu zero is the viscosity at temperature T0, and S is what's called the Sutherland's constant. All temperatures are absolute, so if you need to use this equation, you'd want to make sure that these are in Kelvin, that the temperature is in Kelvin. And Sutherland's constant turns out to be, for air, is 111 Kelvin. Notice that by dimensional homogeneity, these things need to be all temperatures. This whole quantity has to be dimensionless because when we multiply it by mu zero to get mu, this has to be just a constant. So Sutherland's constant actually turns out to have units of Kelvin. And so values for other gases are given in table A2, so we can use this equation to determine the viscosity of a gas, of various gases at different temperatures. Okay? In general, the effect of pressure on viscosity of common gases is minimal for pressures less than 10 atmospheres. And remember, this is 10 times the pressure of air at sea level, so that's a tremendous pressure. But if you get to extremely high pressures, say in some industrial situations, then this might be important. So I think this is the last thing that I want to talk about before we move on to talking about surface tension. But this will be it for this lecture. And I wanted to mention what a Newtonian versus a non-Newtonian fluid is. And so in this case, this line right here, which goes through zero, this is the point 0, 0. This is the rate of shear strain, and this is the shear stress. So if we have a nice linear relationship here that goes through zero, then that equation is going to be for that particular fluid is going to be, the equation of that line will be this. And in fact, any straight line emanating from zero that goes out in any direction would just represent a different viscosity. So Newtonian fluids all have this behavior of having a linear relationship between the rate of shear strain and the shear stress, and basically their intercept is zero. Now we also have other interesting fluids. In this case, we have shear thinning fluids, and some examples of these that are given in the book are like toothpaste and paint. And what we find is that the ratio of the shear stress to rate of shear strain, that ratio of tau over dV dy, becomes less as the rate of shear strain increases. So basically, they're called shear thinning. The shear is getting kind of less and less as we get to higher deformation, quite as it would be. Now, also you can have the opposite. You can have fluids that where this ratio of tau over dV dy get greater as the rate of shear strain increases, and those that would be called shear thickening. And there are also some other strange things where you can have a linear. I'm not sure what a Bingham plastic is, but it's a strange fluid where you have a linear relationship between tau and dV dy, but at when this goes to zero, when dV dy goes to zero, we see that we still have some shear stress, that it doesn't go through zero. So all of these fluids, the Bingham plastic, the shear thinning fluids, and the shear thickening fluids, are all called non-Newtonian fluids. So they do not, for those fluids, tau does not behave like this. It has some other functional dependence, as we can see from this diagram here. In this case, it's going to have a y-intercept, and in this case, it's not going to be linear. It's a non-linear dependence of dV dy on tau. So that's the definition of what a non-Newtonian fluid is. And we will play with a non-Newtonian fluid in class. I will show you one, and you will be thinking about and have to come up with what you think this graph looks like for the non-Newtonian fluid that I'll show you in class. We'll do this as a demonstration in class. Okay, well that does it for viscosity. If we go back, the main thing to remember is that viscosity equals is basically the shear stress divided by the rate of shear strain. This is the shear stress, sorry. This is the shear stress, this is the rate of shear strain, and that ratio is the viscosity. This is the dynamic viscosity, and we will use that a lot throughout the course, and as well as in some cases, some equations will use the kinematic viscosity, which is just the dynamic viscosity divided by the fluid density. Okay,